Hi, this is SM and welcome to our channel Concept of Mechanical Engineering. In the previous class, we have already started our second chapter, which was work transfer, and we have also derived the generalized equation for work for closed system or non-for process work. Now we are going to proceed further. Our chapter was work transfer and we are still studying this chapter. We have seen in work transfer the generalized equation as work done is equal to integration of P dB, in which we have three assumptions. The first one, system should be closed system. And the second one, process must be reversible process. And the third one, work should cross the boundary. These were the three assumptions for this closed system work, integration of PdV. Now we'll see one thing. This is our xy plane. This is x-axis, this is y-axis. If we consider any curve, say this one, so if we project this curve here, the area under this curve, that means this area, this is the area, this is mathematically written as integration of y dx. And if we project this curve to the y-axis, that is this one, then this area, this is the area under the curve on y-axis, is integration of x dy. So same thing we will see in this PdV diagram. This is p axis and this is v axis, and let us consider a process. Say this 1 to 2 is a process. So the area under this curve, this area, this is the area under the curve for the process 1 to 2. This area is mathematically written as integration of PdV. This is the area which we have derived. This is the work done which we have derived for the closed system. So the area under the curve for the process 1 to 2, so for the state 1 to 2, the process is occurring, and this area is the area which is equal to the work done by the closed system. So we can say that area under the curve on of PV diagram on V axis is the work done by the closed system. So the area under the curve of PV diagram on V axis is the work done by closed system. Now let us consider the same graph, that is same diagram, PV diagram, and the same process 1 to 2. If we project this process, this curve on P axis, then this area, the area of the process on P axis, this area is integration of VdP. And if we include minus sign here, then this will be the work done by open system. So area under the curve of PV diagram on P axis with negative sign is the work done by open system. So if we project the area on V axis in PV diagram, then this will be the work done by the closed system. If we project the area on Y axis, sorry, that is on P axis, then it will be the work done by open system. Now let us consider process on PV diagram. This is our PV diagram, and this is a process which is going through state 1 to state 2 via path A and also via path B. So the work done by the process 1A2 can be written as W1A2, and work done by the process 1B2 can be written as W1B2. Now we know that the area under the curve, that is area under the process 1A2, is the work done by the process 1A2 on PV diagram. So this area, this is the area, and this area is the work done by the process 1A2, and the work done by the process 1B2 is this area. This is the area, and this area is the work done by the process 1B2. So it is clear from the graph that the area under the curve under the process 1A2 is not equal to the area under the process 1B2. So these areas are not equal. Since the area is not equal, so work done is different, and work done is different since the states are same but work done is different. That is, it depends upon the path followed. So work transfer is a path function. Though for path A and B, endpoints are same, but work transfer is not same. It depends upon the path followed. Hence, work transfer is a path function. It is not a property. This implies it is not an exact differential. That is, inexact or imperfect differential. That's why we do not write dW not an exact differential. We write del W or d bar W. That is, the differentiation is cut by a line at its top to differentiate an inexact differential from exact differential. Now we will see non-flow or closed system work for different processes. The first one is constant volume process or isochoric process or isometric process. So let us see this with a graph. This is our PV diagram, and let us consider a process which is going through state 1 to state 2 with increase in pressure, or a process which is going through 1 to 2 but the decrease in pressure. In the both the cases, the volume is fixed, that is constant. It is not changing. We know that work done is equal to integration of P dV, and from here, if we see the area under the curve, it is 0. Since the area under the curve is 0, then work done is 0. From graph, we know that we have seen that this area is 0, and so work done is 0. And if you see mathematically, work transfer is equal to integration of P dV, and this is only valid when the system is closed system, process is reversible, and work should cross the boundary. Since here volume is constant, then the change in volume will be 0, that is dV is 0. So W is equal to integration of P dV, in which dV is 0, therefore work done is equal to 0. So for constant volume pressure process or isochoric process or isometric process, work done is 0. It is clear from the graph, the area under the curve is 0, and we know that the area under the curve on PV diagram on V axis is equal to the work done by closed system, so work done is 0. Now we will see the next process. Second is constant pressure process or isobaric. It is also called as isobaric or isopiestic. So this is our PV diagram, and let us consider a process which is going through state 1 to state 2. This is for expansion. Since the volume is increasing with constant pressure, so it is expansion, or process 1 to 2 in which volume is decreasing, so it is compression. In both the processes, this is 1 to 2, pressure is constant but volume is increasing, so it is expansion, and here in 1 to 2, pressure is constant but volume is decreasing, so it is compression. It is clear from the graph that the area under the curve is not 0. It may be positive, may be negative. So this work done may be positive, may be negative. Let us see. W is equal to integration of P dV. Since pressure is constant, it will get out of the integration. So W is equal to P into dV, and we know that integration of dx is x. So from here, and this is from state 1 to 2, so P into integration of dx is x, so integration of dv will be v from state 1 to 2. So work done is equal to P into v2 minus v1. This is the formula for work done for constant pressure process. So since pressure is constant, it is out of the integration, and we have got the value W is equal to P into v2 minus v1. This is work done for closed system. Now this is our PV diagram, and this is the expansion process from 1 to 2. Work done by this process 1 to 2 is equal to P v2 minus v1. Since volume 2, that is v2 is greater than v1, so this term will be positive. This implies work done by the process 1 to 2 is positive. So for case of expansion, the work done will be positive. and this is the area under the curve. This area always take area always magnitude, and the sign is positive sign is due to the expansion process. Since volume is increasing, so the work done is positive. Let us consider the same example, PV, but here the process is compression process 1 to 2. So the work done will be for 1 to 2 P V2 minus V1, and V2 is less than V1. Since V2 is less than V1, because volume is decreasing here, so final volume is less than initial volume, so this term will be negative, this will be negative, and hence work done 1 to 2 is negative. That is, this is the area for the work done. Area always magnitude. So for the case of expansion, the work done will be positive, and for the case of compression, the work done will be negative. In the formula, work done equals to integration of P dV P into V2 minus V1, sign already included, sign already included. If the process will be expansion, then V2 will be greater than V1 and you will get a positive work done. And if the process will be compression, then V2 will be less than V1 and you will get the negative sign. So for this formula, you do not have to care about the sign. Whatever the process will be, you will get the result according to that one. If it is expansion, you will get the positive work, and if it is compression, you will get the negative work. Now the third one is isothermal process. The PV diagram for isothermal process is like this: is P, this is V, and this is a process from state 1 to state 2. This is an expansion process. Since volume is increasing, it is expansion, or this is a process which is going through state 1 to state 2, but volume is decreasing here, so it is compression. So we know that this work done is equal to integration of P dV, and we have assumptions here. The first one, closed system should be closed system. The second one is the process must be reversible process, and the third one, work should cross the boundary. These are the assumptions for this work done by closed system. Now, since we know that PV equals to mRT, this is from ideal gas equation. From ideal gas equation, we know PV equals to mRT. Since it's a process of, it is an isothermal process, that means constant temperature process. So T is constant here, M is constant, R is constant, and here T is also constant. So we get PV equals to constant. Now we will get the value of P as C by V. Putting the value of P from this to here, we will get the work done as integration of C by V dV. This implies W is equal to integration of C will get out of the integration, because C is a constant, it will get out of the integration, we will get dV by V. We know that integration of dx by x is ln x, that is log of x. So from here we will get work done is equal to C into ln V, and since the process is from 1 to 2, so we will put the integration limit from 1 to 2. From here we will get C ln V2 minus ln V1. From here we will get W is equal to C ln V2 by V1. We know that ln m minus ln n is equal to ln m by n. So work done is equal to C ln V2 by V1. Since PV equals to constant, we can get that P1 V1 equals to P2 V2. So in place of C we can put P1 V1. V2 by V1, or this work done is equal to P2 V2 ln V2 by V1. Or this is equal to MRT ln V2 by V1. From here we will get P1 by P2 is equal to V2 by V1. So we can substitute the value of P1 by P2 here. We will get MRT ln P1 by P2. So for isothermal process, this is the expression for work done. Now for this equation there is assumptions. The first one is, because this is derived from the equation PV equals integration of PdV, so the system should be closed system. Process must be reversal process. The third one, work should cross the boundary. And the fourth one, because we have used ideal gas equation here, so the fourth assumption is ideal gas. So this is the work done for isothermal process with those assumptions. System should be closed system, process must be reversal process, and work should cross the boundary, and the fourth one is ideal gas equation. Gas should be ideal gas. Now the fourth process is adiabatic process. Adiabatic means there is no heat transfer. There is no heat transfer. If you see this graph, the process is represented in PV diagram as this is a process from 1 to 2. This is for expansion, and this is for compression. Since the volume is increasing here, so this is expansion process, and volume is decreasing here, it is compression process. We know that work done is equal to integration of P dV with the assumption closed system, reversal process, and third one, work should cross the boundary. So with this assumption, we have integration of P dV, work done equals to integration of P dV. Adiabatic, this implies P rho gamma equals to constant. We cannot write like this because this is only possible. This is adiabatic means only no heat transfer. That is, heat transfer is 0. We can write PV to power gamma equals to constant only PV to gamma equals to constant when the process is reversible process and the gas is ideal gas. If we fulfill these two conditions, then only we can write P to gamma equals to constant. We cannot directly write here P to gamma constant. Adiabatic means P to gamma constant. We cannot write like that. We can write this equation P to gamma equal constant only if and only if that reversal process and ideal gas equation. W is equal to integration of P dV, and for reversible adiabatic process PV to power gamma equals to constant. We can write P is equal to C by V to power gamma. If we substitute the value of P from here to here, we will get W is equal to integration of C by V to power gamma into dV. V is equal to, C is the constant, so it will get out of the integration, C into integration of dV by V to power gamma. This we can write as W is equal to C integration of V to the power gamma minus, V to power minus gamma into dV. And we know that integration of x to the power n is dx is equal to x to the power n plus 1 by n plus 1. So integrating, we will get the value work done C into, and since we have considered the process from 1 to 2, we will put the limit as 1 to 2. So it will be V to power minus gamma plus 1 by minus gamma plus 1 from 1 to 2. Here we will get W is equal to C into V to power 1 minus gamma by 1 minus gamma 1 to 2. If we put C inside, we will get C into V to power 1 minus gamma by 1 minus gamma 1 to 2. W is equal to, this we can arrange like this, C by V to power gamma into V by 1 minus gamma, because 1 minus gamma means V to power 1 minus gamma is equal to V by V to power gamma. So we know that C by V to gamma is equal to P. So we can put here, in place of this, we can put PV by 1 minus gamma from 1 to 2. This is P2 V2 minus P1 V1 by 1 minus gamma. And if we take minus from common from here and put here, we will get work done is equal to P1 V1 minus P2 V2 by gamma minus 1. This is the equation for work done by adiabatic process. And here are the assumptions, that is reversible, adiabatic and ideal gas. So for this equation we will have the assumption as first one, closed system, second, reversible adiabatic reversal process, the third one, work should cross the boundary, and the fourth one is ideal gas. So this equation is only valid if the system is closed system, process is a reversible adiabatic process, work should cross the boundary, and ideal gas is there. Here gamma is adiabatic index. Note one thing, P to a gamma equals to constant. This is applicable for both system, open or closed. So for both system, open and closed system, we can assume this P to a gamma equals to constant. Adiabatic process is also known as isentropic process. So adiabatic process is also known as isentropic process. Sorry, reversible adiabatic. So reversible adiabatic process is also known as isentropic process. So reversible adiabatic process is an isentropic process. Now the fifth one is polytropic process. Polytropic process. Polytropic means there is heat transfer, there is work transfer, and we have PV to power n equals to constant without any assumption. So there is no assumptions. Now this is the PV diagram for polytropic process. 1 to 2 with there is an increase in volume, so it is expansion, and 2 to 3, sorry, 1 to 2 this, there is decrease in volume, so compression. We know that work done is equal to integration of P dV, and PV to power n equals to constant. From here we will get the value of P as C by V to power n. We will substitute this value to this equation, then we will get the work done as integration of C by V to power n dV. In the same way as we have calculated the value of work done in adiabatic process, we will get the value here P1 V1 minus P2 V2 by n minus 1. This is the work done by a polytropic process with the assumption system should be closed system. Process must be reversible process. And third one, work should cross the boundary. This is the work done by a polytropic process. P1 V1 minus P2 V2 by n minus 1. Adiabatic means no heat transfer. Isentropic means no heat transfer plus reversible process. Isentropic plus ideal gas, we have PV to power gamma equals to constant, and for polytropic process there is heat transfer, there is work transfer, and PV to power n equals to constant without any assumption. So adiabatic, if it is adiabatic, then there is no heat transfer. If it is isentropic, then there is no heat transfer plus reversible process, then only isentropic. And if it is isentropic plus ideal gas, then PV to power gamma equals to constant can be applied. For polytropic process, there is heat transfer, there is work transfer, and PV to power n equals to constant without any assumption. For polytropic process, n is the polytropic index, and its value lies between minus infinity to plus infinity. But for practical purpose, it is taken as 1 to gamma. Since the value of n lies between minus infinity to plus infinity, so for practical purpose it is between 1 to gamma. Isolated system. There is no heat transfer, there is no work transfer, and there is no mass transfer. Now slope of isothermal curve on PV diagram. So let's see the slope of isothermal curve on PV diagram. This is our PV diagram, and this is isothermal curve. So the slope means tan theta dy by dx, tan theta. This is tangent. Then this tan theta is the slope, and this is perpendicular by base. Perpendicular, this P is, and in base V is there. So dP by dV. So slope is equal to tan theta is equal to dP by dV. So this is our isothermal curve, and this is the slope. dp by dv. Now we know that from ideal gas equation PV equals to mRT, ideal gas equation. M is constant, R is constant, and since the process is isothermal, T is also constant. This implies we will get V equals to constant. If we differentiate both sides, we will get P into dV plus V into dP is equal to 0. This implies P dV is equal to minus V dP. This implies dP by dV is equal to minus P by V at T equals to constant. Therefore, dP by dV at constant temperature is the slope, and this is minus P by V. So, this is the slope of isothermal curve on PV diagram. Now, dP by dV is equal to minus P by V. This is always positive. Pressure is always positive, and volume is also always positive. So, this will be dP by dV. This implies dP by dV at T equals to constant is always be negative. So the slope of isothermal curve will be always negative. Negative always. And this negative curve is clockwise. This negative slope is clockwise. We know that this is y, this is x. Let us consider one these two lines. Then this slope is negative. This is clockwise slope, so negative. And this is anti-clockwise slope, so positive. So clockwise slope is negative and anti-clockwise slope is positive. So this is the slope dy by dx, and slope of isothermal curve is always negative. So slope of isothermal curve on PV diagram is always negative. A slope of adiabatic curve on PV diagram. This is our PV diagram for adiabatic process. For isentropic process, PV to power gamma equals to constant. Slope equals to this dP by dV. Now, differentiating both sides, we get T into differential of V, gamma times V gamma minus 1 into dV plus V to power gamma into differential of P. This is dP is equal to 0. Now, P into gamma V to power gamma minus 1 dV is equal to minus V to power gamma dP. This we can write V into gamma V to power gamma by V, because V to power gamma minus 1 means it is V is in bi form. So dV is equal to minus V to power gamma. This is dP. Now, dP by dV is equal to this V will cancel out, so it is minus V by P into gamma. This is the slope for isentropic process. This is positive and this is always positive, so the slope will be negative. So dp by dv adiabatic is equal to minus gamma times p by v, and we know that the slope of isothermal curve on PV diagram is minus p by v. If we substitute this value here, we will get dp by dv adiabatic is equal to minus gamma times dp by dv isothermal. So slope of adiabatic curve on PV diagram is gamma times greater than the slope of isothermal curve on PV diagram. Hence slope of adiabatic curve on PV diagram is gamma times greater than the slope of isothermal curve on PV diagram. So slope of adiabatic curve on PV diagram is gamma times greater than the slope of isothermal curve on PV diagram. Slope see, we have two different curves. Here this is for expansion and this is for compression on PV diagram. So identify which curve is for isothermal and which curve is for adiabatic. We have seen that the slope of the adiabatic curve is gamma times greater than the slope of the isothermal curve. See, what is the slope here? This is the slope. This is the slope. This slope is greater than this one. See, this is the slope for this one and this is the slope for this one. If we measure the angle of the slope, then theta is greater here compared to this one. See, this is having this slope and this is having this one. It is like that and it is like this. So this slope, this is greater than compared to this one. It is less. So this is adiabatic expansion. And this is isothermal expansion. Now for this case, compression, this is the slope and this is the slope for this one. See, clear it is from the graph that the slope, this is less because it is making less angle theta compared to this one. This is greater angle. See, this is greater angle and this is less angle. So this is isothermal compression and this is adiabatic compression. So this is the difference between the curve of adiabatic and isothermal process. Now PV to the power k equals to constant. This implies if the value of k is 0, then if the value of k is 0, if we put here 0, then v to the power 0, then the value of this will be 1. So this implies p equals to constant, and p equals to constant is a isobaric process, and if we put k equals to 1, then k equals to 1 means PV equals to constant. This means isothermal process. Isothermal process. If k equals to n, this implies PV to power n equals to constant. This is polytropic process. Now, if k equals to gamma, this implies PV to power gamma equals to constant. This is adiabatic process. Adiabatic process. If k equals to infinity, this implies k equals to infinity, PV equals to PV over k equals to constant. If we put k equals to infinity, before that raise both sides to the power 1 by k, then p to power 1 by k into v to power k to the power 1 by k, c to the power 1 by k. P to the power 1 by k, v to the power k to the power 1 by k is equal to v. C to the power 1 by k is another constant, c dash. V is equal to c by p to the power 1 by k is equal to c dash by p to the power 1 by infinity. 1 by infinity is equal to 0. So c dash by p to the power 0 is equal to c dash. This implies v is equal to c dash is equal to constant. So if k equals to infinity, then v equals to constant. This implies this is constant volume process, that is isochoric process. So in this general equation, p to the power k equals to constant, if we put k equals to 0, it will be isobaric process. If k equals to 1, then it will be isothermal process. If k equals to n, then it will be polytropic process. If k equals to gamma, then it will be adiabatic process. And if k equals to infinity, then v will be constant and it is isochoric process. Now we have two graphs here, one for expansion and other for compression. PV and PV diagram. We have seen that PV over k equals to constant. We have seen the different condition by putting the value of k. So if k equals to 0, then it is constant pressure process, so isobaric process. So here k equals to 0 will represent this line. If k equals to infinity, then it is constant volume process, so this is for k equals to infinity. Now we know that for polytropic process, N lies between 1 and gamma for practical purpose. So this is k equals to n. Now these, out of these two curves, one is adiabatic and one is isothermal. We have seen that the slope of adiabatic curve is gamma times greater than the slope of isothermal curve on PV diagram. So this is the slope for this curve and this is the slope for this curve. So this slope is greater than compared to this slope. So this is k to power gamma, that is adiabatic process, and this is k equals to 1, that is isothermal process. Now for compression, k equals to 0. This is for k equals to 0, which is isobaric process. For k equals to infinity, which is constant volume process, which is isochoric process, this is k equals to infinity. Now we know n lies between 1 and gamma for practical purpose, so this is k equals to n. Now out of these two curves, one is adiabatic curve and one is isothermal curve. We know that the slope of adiabatic curve is gamma times greater than the slope of isothermal curve. So this is the slope of this curve and this is the slope of this curve. So this slope is greater than compared to this slope. So this is adiabatic, k equals to gamma, and this is, it is less, so k equals to 1, which is isothermal. In case of polytropic process, for practical purpose, the value of n lies between 1 and gamma, and so k equals to n lies between k equals to 1 and k equals to gamma. That is, the curve of polytropic process lies between isothermal curve and adiabatic curve. Now ideal gas equation for various processes. First one is constant pressure process. PV equals to mRT from ideal gas equation. Since pressure is constant, this implies V is directly proportional to T. This implies V1 by V2 is equal to T1 by T2. This is Charles' law. Now, second process is constant volume process. We know PV equals to mRT. Since V is constant, this implies P is directly proportional to T. Therefore, P1 by P2 is equal to T1 by T2. This is Gay-Lussac law or Amundsen's law. Now, third one is isothermal process. PV equals to mRT. Since T is constant, then PV equals to constant. This implies P is inversely proportional to V. So P1 by P2 is equal to V2 by V1. This is Boyle's law. Now Avogadro law. For given pressure and temperature, V is directly proportional to N, where N is number of moles, or V is directly proportional to M, where M is the mass. Now fourth one is adiabatic process. Here we have PV over gamma equals to constant and PV equals to mRT. From these two, we have P1 V1 is equal to P1 V gamma is equal to P2 V2 to the power gamma. P2 by P1 is equal to T2 by T1 to the power gamma by gamma minus 1. T2 by T1 is equal to V1 by V2 to the power gamma minus 1. Now fifth one is polytropic process. PV to power n equals to constant, PV equals to mRT. From this two, we have P1 V1 to power n equals to P2 V2 to the power n. P2 by P1 is equal to T2 by T1 to the power n by n minus 1. T2 by T1 is equal to V1 by V2 to the power n minus 1. If you find this video helpful, please like, subscribe and share it with your friends. Thank you for joining me today. See you in the next class.